Okay, so looking at the warm-up here, doing a little more practice with our energy diagrams. Reminder, when you're doing the energy diagrams, you're always going to have time or you'll see something with the something with the reaction, like the timing of the reaction on the x-axis. Your y-axis, you'll see it written a few different ways. Sometimes you'll just see energy. Other times you'll see potential energy. Other times you'll see enthalpy, which is a measure of heat. Or sometimes you'll just see H. Technically, those aren't all the same thing, but think of them as the same. Like for our purposes, when you're interpreting these energy diagrams, it's a similar concept. So just be kind of aware of those different forms the y-axis will take. And then they're giving us some points. So they're telling us here the H, or the enthalpy of the products, is 60 kilojoules. So what's telling you is, if we let this be 0, and if we have to get up to 100, maybe we make this 100. So let's say 60 is about right there. At 60 kilojoules, I will have my line for products. Okay? Now, different ways you can try and interpret this. You could then go to, we can look at delta H. If delta H is positive 30 kilojoules, if keyword is on positive, that means the products are 30 higher positive going up than the reactants, than the H of the reactants. So what would the H of the reactants be then, considering our delta H is 30? If you were to get more like mathy with it, you would say, because delta H equals final, or your products, minus initial, or your reactants. So 30 kilojoules equals our final, which are products, 60 minus X, which would be the H of the reactants. So what would H of reactants be? 30, good job, athletes. 30 kilojoules. So H of reactants is 30 kilojoules. So what that means is, at 30, we would have a line here, and that would signify, shorten a little bit, that would signify where our reactants are at. Now then, we got to include the activated complex. So what this is telling us here is that we're going to rise until the very peak of the hill is at 100 kilojoules. Okay? And then what goes up must come down, but then now we're gonna end our journey at the 60 kilojoules where the products are at. Okay? So they'll change kind of what piece of information they give you, but you just kind of gotta, stay calm. Just try your best to interpret what they're saying. Now, if we were to kind of ask some other questions with this, what would be my my activation energy? Thoughts? Huh? 60. Not 60. Huh? 70, yeah. Because you start at the very bottom, which is 30, where the reactants are at, each of the reactants. Go toward the activated complex at the top of the hill, and that difference between 100 and 30 would be 70 kilojoules. Okay. What would be the activation energy for the reverse? We go from here to there. Here? Yep. 40, yeah, good. Yep. Because now you're starting here at 60, and you're going up to 100. So now it's not negative 40. Some people are saying that just because you're going, from products or from right to left. Well, and when you're doing the reverse reaction, the products are now your reactants, and your reactants are now your products. When you're going this way, that isn't. You're still going up. You're still adding an energy, so it's not negative. What would be the delta H of the reverse reaction? Last one on this. So if I'm going in the reverse, so starting here and going to what were my old reactants, what would be my delta H now? Negative 30, good. So on the delta H, you're reversing the sign. Because delta H is the difference between the enthalpy or the products and enthalpy of the reactants. No matter if I go here to there or there to there, I still have the same magnitude. The number 30 will still stay the same, but depending if I go down or up will be the sign. If you go down, if you start higher and you end lower, that's when you're negative. Okay. All right. So, I mean, that's really about all the, like, if you understand this, I mean, you understand a lot when it comes to energy diagrams. There's not too much more people are going to ask you about. Drawing them is the most difficult thing to do. So if you can understand how to draw them, you're in a really good spot. Okay. So getting into entropy, let's talk about your bedroom. So, you know, there's a reason, like, nobody's parents in the history of the world, I imagine, have asked them, hey, can you go make your room look like this? Can you make your room make your room be really, really messy? They tell you to clean up your room. Now, the reason is because kind of the natural order of things is things get disordered, like your bedroom. If you don't actively, like, put in effort, your bedroom will look like this. Or like showering and fixing your hair, right? Like, I didn't just wake up like this, right? I had to actually, like, do my hair, put on my makeup, you know? Like, I actually had to put in effort to look like this, you know? Like, it doesn't, believe it or not, some of you are like, really? Anyways, and that's really, like, what we actually see, like, as, like, an actual, like, a law that can apply to the whole, like, study of, like, chemistry and physics and stuff, is that things want to move towards what we call higher entropy. Entropy is essentially a measure of the randomness or the amount of disorder in a system. And it's just saying that nature wants to go towards a randomness. Okay? So bedroom, high entropy, you know, like your bedroom. You know, I don't know whose bedroom this is. Not mine. But this would be low entropy. Okay. So what does this look like in chemistry speak? Well, if we're looking at what high entropy would look like if we're talking about molecules and stuff, this would represent high entropy. When the particles are, like, not clustered together, when they're randomly spaced throughout. And I think to understand that, I think it's helpful to look at what low entropy would look like. Low entropy would look like a high amount of order, right? In other words, high order, low disorder. So if things are really organized, like, for example, you, like, literally a human being, any living thing, that is a highly ordered thing, right? You have very low entropy as a human. That is why you have to eat things. You have to keep eating things to maintain your body. Otherwise, you know, when you die or anything dies, eventually they will decay into disorder, right? The organized cells that make all of us up will eventually break apart into the individual atoms and molecules that make us up, and those will disperse, spread out, be highly disordered throughout the environment. Okay? Yeah, so entropy, a measure of chaos, is another word you'll hear it said. It's a measure of chaos. So high chaos would be high entropy. An abbreviation for entropy is the letter S. So if you see, a lot of times you'll see it written as delta S. Remember that delta is final minus initial. So if you're measuring delta S, you're looking at the change in entropy. How is entropy changed when you do a chemical reaction? And when they say system, you'll hear that word in chemistry and especially in physics. System is basically like the environment that you're, like, doing the experiment in. So, like, if you're doing a reaction in a test tube, that test tube would be your system. Okay. All right, we good here? All right. Now, there's something called the second law of thermodynamics. The second law of thermodynamics is basically a law about entropy. It's saying that if you're looking at an isolated system, So basically, we're looking at the entire universe. Second law of thermodynamics is saying that entropy in the universe is always increasing. So delta S, I wouldn't say delta S, but entropy of universe is increasing. The universe is moving towards a state of higher disorder instead of higher order. Let's take an example of like getting into more chemistry speak, what this would look like if you're doing a reaction. Let's say you're doing a combustion reaction where you're going to take a solid block of wood and you're going to burn it like you're doing a campfire. Well, we learned when you do a combustion reaction, every time you do combustion, you make carbon dioxide and water. Now, I think we can all agree that all of these individual carbon dioxide molecules and H2O molecules, these are way more disordered than compared to a solid block of wood. There is more order here, more order. So lower S, lower entropy. Here, less order. So higher S, higher entropy. Okay? So if we're looking at a chemical reaction, if entropy increases, we say it is a favorable process. Favorable means the universe wants that to happen. You don't have to really put in a whole lot of energy to make that reaction happen. Burning of like a tree, like once you get that spark going, like think of a forest fire, it unfortunately will just spread because that reaction, that chemical reaction of burning wood is a favorable reaction. It's increasing the entropy of the universe. So once it gets going, it's going to keep rolling until you run out of that fuel source. Now, the opposite of that would be if you decrease the entropy, if you do a chemical reaction that creates order. For example, when you're making a chemical reaction where you eat your food, like you eat your food and you break your food down into like amino acids, some fats, some carbs, some nucleic acids, and you use those call them biomolecules to build to build up your cells and keep you ordered. That process where you take these building blocks to maintain you, that would be not a favorable reaction, not a favorable process. That's why you need to eat calories and have an energy source. Talk about ATP. You got to have energy to make those reactions happen. Okay. Moving forward to kind of some more of like questions you would see on the worksheet today or even on a test is let's say I gave you, for thinking states of matter, let's say I'm comparing ice versus liquid water. We would say that ice, because it is more ordered, ice, what would it have? Would that have more entropy or less entropy? Was it? Less, yeah. Lower S. Good. More order, so lower entropy. It's backwards. I think it's the thing with entropy. It's always back. You would think that like in our society, if like, hey, that person's really stable. It's a stable person. You would not think like they would be like organized, well put together, and you would think that's what you want. The universe doesn't want that. The universe wants this: high entropy, high disorder, where the particles are moving around faster and randomly. It's another keyword, random. It's random, like these arrows are just randomly placed there. Okay? Anyway, so liquid water would have higher entropy, ice would have lower entropy. So if you move from solid ice to liquid water, you are going to have a positive, a greater than zero, delta S. So another way of saying that is delta S is positive. If you're greater than zero, you're positive. So if you break anything, any sort of particle, into smaller pieces, you do a chemical reaction where you break a larger thing into smaller things, that is a positive delta S. You have increased entropy. The universe wants that. So this is favorable. We good so far? Give me a minute to finish writing. Okay. Let's look at, it's really kind of building on the same example. like talking about solid to liquid, but it's taking it a little bit further, talking about gas. If you are moving from a solid to a liquid to a gas, you are increasing entropy. In other words, the delta S is becoming positive. This is favorable. It's favorable because you are increasing your entropy. Now, why that is for a similar reason. If you start with the solid, it's what we saw with ice going to liquid water, right? This is more ordered. This is less ordered. This is, you could say, less disorder. You know, this is more disorder. This is the most amount of disorder. So as you keep moving, you are going this way. You're going to be increasing. Your delta S becomes positive. Now, think if you go the other way. If you go from a gas to a liquid to a solid, the delta S is now lower than 0. So now here, delta S is negative. Here, delta S is positive. Going from a gas to a liquid to eventually a solid, that is going to be decreasing in entropy. So this is not favorable when you're going this way. Okay? What that means, you would have to add energy to make this happen. It's not a favor, like the universe doesn't want that process to happen. Good so far? Okay. Last kind of situation that's going to increase entropy is, and it's using the same picture, it's if temperature increases. Because think about it. If you have like a solid, if you have like an ice cube, if I want to make that ice cube go to liquid water and eventually into water vapor, all of which is going to give you a positive entropy, positive delta S, I need to add energy, add temperature to make that happen. I need to increase the temperature in order to get a positive delta S. So increasing temperature, that's going to go with a higher amount of entropy. Another way of thinking about that is like when you measure temperature, if you measure something that's really hot, you're measuring how fast are the particles moving. The faster the particle, the higher the temperature, like in a gas, particles moving around faster, more movement, faster things are moving, that goes with a higher amount of disorder, which is why that's going to be an increasing entropy. Okay. All right. So let's look at some more practice type problems you would see. So here they're giving us a reaction where basically ammonia and some oxygen makes nitrogen monoxide and some H2O, and they're going to ask you, hey, what is my delta S here? Now, I have it filled in. I'm telling you it's positive and positive, but they would ask you, is that positive or negative? And how you would figure that out is you are going to look at the number of products compared to reactants. What I mean by that is you want to focus on the coefficients. You want to add up the coefficients. So in other words, if I give you this reaction, you need to make sure the reaction's balanced, right? So here's a balanced reaction. Add up the coefficients of your reactants on the left side of the arrow. So in this case, 4 plus 5 is 9. And then compare that to the coefficients on the right side in your products. Here, 4 plus 6 is 10. So what that means is I made more particles on my products than in my reactants, so that is why my delta S is positive. Okay? If your coefficients are higher on your products than your reactants, that's a positive delta S. You have increased entropy. You have broken a bigger thing into smaller things. Another example, we're looking at this reaction here. I have just one reactant, and you see no number in front of that. That means the coefficient there is 1. If you look at your products, you have a coefficient of 2. You made 2 nitrogen dioxide molecules, so you went from a 1 to a 2, so that is a positive delta S. You have increased the amount of disorder, so you have increased the entropy. Okay, let's try. Let's go over these few down here. So this one, if I gave you H2O, liquid water, this is an L, going to G, gaseous water, that would be a positive delta S. I showed you like on the last slide, right? If you go from a liquid to a gas, the particles are moving faster, so that's a positive delta S. If we look here, CO2. If I go from CO2 gas to aqueous CO2, remember aqueous means it's dissolved in water. So aqueous, what state of matter is aqueous? Solid, liquid, gas? Victor? Liquid. Okay, so you're going from a gas to a liquid. So you're going from gas, particles are further apart, more randomness, to less randomness, or closer together in a liquid. That's why it's a negative delta S. Okay. Down here, this would be this one would be where you're just going to be comparing the coefficients. So I have 2 sulfur trioxide molecules make 2 sulfur dioxide plus 1 oxygen. So in my reactants, I have a coefficient of 2. In my products, I have a 2 plus a 1. So 2 plus 1 is 3. 3 is more than 2. So what that tells you is that I have created more disorder, so I have a positive delta S right now. Is it making some sense? All right, last one. Sodium chloride, NaCl. I took NaCl and I made, so I have a 1 for my coefficient, and I made 2 separate things. I took a chunk of salt and broke it into the separate pieces. So you went from 1 to 1 plus 1, so that's a 2. So you went from less to more, so that's why it's a positive delta S. Are we good? We got questions? Okay, so you got the rest of that worksheet. It's fairly short. There aren't too many more problems I would give you on that, but if you're a little behind on that reaction rate lab from last class, you could have some time to finish that up as well.